All right, and welcome back for the second half of Climate Change Part 2. Hopefully you've listened to the first half of this video, and let's get on with the conversation. So now understanding CO2, let's understand, first of all, what the current levels are, okay? So the current levels, this paper keeps falling. The current levels are about 400 parts per million, so we're right at 400 parts per million. And that's actually a pretty low point considering what CO2 levels have been historically on our planet, okay? So prior to the O2 expansion, prior to plants being here on Earth, there was massive amounts of CO2 in the atmosphere, probably about 200 parts per million. 200,000 parts per million CO2 in our atmosphere. Now that kind of fell over time as volcanic activity went down, and you ended up with plants consuming the CO2 and turning that into oxygen. Then our oxygen levels came up, and then you ended up with animal life forming. So animals started actually consuming the oxygen, producing CO2. But there's this kind of slightly negative balance in the total equilibrium, meaning CO2 levels have dropped. Now, CO2 is really important for a healthy biosphere, and this is because, as we just talked about, plants consume it as a part of photosynthesis to live. So our planet is the green planet, and well, the blue planet, but it's a very green planet compared to other planets because we're the only ones with plants as far as we know. And that's because we have CO2. So CO2, I really hate how people demonize CO2. Oh, CO2 is this whole horrible evil thing. Well, it's not, actually. CO2 is the lifeblood of this planet because it is what has allowed all plant life on this planet to form, period. Okay, you need CO2. But there is a higher level, right? There is too much CO2, and that's not the current concern with climate change. People like to think about, having this runaway greenhouse effect and how the end of the world will happen, but we can get into the data in a little bit on why I think that's probably not going to happen. But, up until about 4,000 parts per million, humans and animals live really, really well because plants thrive, okay? And so let's kind of look at this. So I want to look at how CO2 affects plant life, how it affects animals, how it affects our oceans, what happens when there's too little CO2, and then what happens when there's too much CO2, and can you end up with a runaway greenhouse effect, okay? So first off, CO2 in terms of plant life. So we look back about 30 million years ago, and there's a genetic change in the metabolisms of plants. So prior to 30 million years ago, there was typically over 800 parts per million of CO2 in the atmosphere. And then at that time period, it dropped below 400 parts per million. Now, this caused a genetic change that's called from a C3 metabolism to a C4 metabolism for plants. Plants that are in the C4 category, they make up about 15% of the biosphere, and they do extremely well between 400 and 1,000 parts per million of CO2 in the atmosphere, okay? And again, these started showing up about, 30 million years ago. Now, the other plants, the C3 plants, which make up 85% of our biosphere, they do really well between 1,000 and 2,000 parts per million in terms of CO2 in the atmosphere, which means they are not doing super well based on the global CO2 averages, okay? They are minimized, there's a lot of variation across the planet, but they don't typically do well. This 15% does really well at the current CO2 levels. Okay, now most of our food supply is actually in that C3 level. So most C3 plants are what humans eat for food as our primary food consumption. Now, if our current levels are 400 and most plants, especially our food, does better between 1,000 and 2,000 parts per million, then what's the problem with raising CO2 levels? Well, again, it goes back to the short period of time that we're going to increase temperatures and not allow civilizations to adapt, or ecosystems to adapt. But what does that mean for the plant life on this planet? Well, it means that plant life is going to get significantly better. So let's take a quick look at the last 200 years, okay? So in the late 1800s, early 1900s, plants weren't doing very well on this planet because CO2 levels were, down in the 300 levels, or 300 parts per million, okay? And so there wasn't a ton of growth across the planet plant-wise. We were coming out of an ice age. All right, we've been coming out of an ice age for the last couple thousand years, and the planet is getting warmer, which is good. So plants are doing better, but they're not doing as well as they could, right? And so the other thing that happened is humans. So we started burning trees for fuel in our houses, and so we started cutting down a lot of tree life. And so as the human populations over the 1900s started growing, we started seeing mass deforestation as we started cutting down more and more trees, literally just burning all of them for fuel to keep our houses warm, as well as building supplies and all the other things that we use wood for. Okay, so somewhere in the the 1940s to 1950s, we started shifting a huge major shift across the entire country. You could probably argue that it started more down at the 1930s. We started shifting more to coal. Okay, and oil and gas production. So then we started oil and gas production. Well, we started drilling and mining for these types of things, and we started cutting down less trees. So we had less of an impact on trees because we started moving away from trees as a primary fuel source. Well, it's even done better today. So in the last 30 years, we almost don't use trees from the wild. Most trees are sustainably farmed. There's many countries across the planet that are actually planting trees, so we end up with more forests. So what is the net result of changing technology away from burning trees, so that now we're on nuclear as well as solar and wind, as well as all these other potential renewables in the future? What does that mean? Well, it means that the planet has actually gotten a lot greener. Now there's two parts to that green piece. So there's the part that we stop cutting everything down, and then there's also the part that humans have been dumping massive amounts of CO2 in the atmosphere. So this has had a positive effect. And so here's a graph from NASA that shows over the last 100 years, we have increased the total biosphere of plant life on planet Earth. This is just data. Take it for how you want, okay? But we've increased the equivalence of an entire Amazon rainforest across the entire globe. Now that's 5% across the globe. That means where you live, there's 5% more plant life from year to year. That's in North America, that's in South America, that's in Asia and India and all Europe. So you probably haven't noticed the 5% change. Maybe you've noticed that summers are a little bit greener, but you haven't noticed too much beyond that. But that 5% equates globally to an entire Amazon rainforest. And I'm going to tell you this, based on the data from NASA, that's just going to continue. The world is going to get greener and greener and greener over the next several hundred years because we keep dumping CO2 in the atmosphere, and all of the vegetation on this planet consume that CO2. So that's positive. That is not bad. But there's also other positives that come from that. Because we are restoring natural habitats, because humans are backing out of them and actually replanting trees, in addition to the fact that there's just more greenery in general, there are plenty of people and scientists that have noted that many species that we thought were endangered are actually coming back. There was a recent study in China that was discussing this, where they found the largest population ever of snow leopards that they thought were mostly completely extinct. And they found them, and they were very surprised that they had come back. In addition to that, China has found that golden pheasants and red foxes and roe deer, they're all coming back in staggering population numbers, specifically because all of their forests are getting greener and humans are kind of just leaving them alone. Okay, so there's huge positive impacts to the planet based on rising CO2 levels. So CO2 levels are good for planet Earth. Okay, now where's the upper limit? Well, we don't know. I mean, we do know based on how CO2 affects animals and plants. So again, the plants typically do well between 400 and 1,000. Those are those C4 metabolism. 1,000 and 2,000, those are those C3 metabolism plants. Humans typically can do okay. In breathing inside in a house with a lot of people is probably about 2,000 parts per million on average. The global NASA recommendation for a daily dose of CO2 is about 9,000 parts per million. So you're talking about substantially higher levels of CO2 than we have now. And since the global average is increasing about 2.5–3% per year at the current rate, you have a long time until you hit those unhealthy limits. So you have this huge range from 400 parts per million where we are now to about 2,000 parts per million, where there's a huge positive impact to most of the biosphere on this planet. That's a huge range. And it also means that we have a lot of time to try to curb that exhaust of greenhouse gases to minimize our impact on the temperature. there is positive growth in that time period. There are good things. And the reason I bring this up is because I can't tell you how many times I've heard the argument for, hey, we need to create these huge scrubbers to pull as much CO2 out of the atmosphere as possible, or hey, how about we throw nanites out there? Okay, well, the problem is there's a lower limit where CO2 is too little CO2 is very dangerous for this planet, and we'll get to that in a minute. So again, higher levels of CO2 in the atmosphere, more green, more animals, the plant life as a whole seems to be doing really well with higher levels. But what does that mean for our oceans? Because you've heard of ocean acidification. Back in the 90s, you had Al Gore and a whole bunch of climate activists that were really concerned with the acid levels in the ocean. And so they did a bunch of early experiments in the 90s where they increased the acid levels with a bunch of animals in an aquarium, and most of these acid levels just ate away all the shells and a lot of the calcification as a part of those animals, and they just didn't do very well. They died. However, there has been quite a few interesting studies that have been going on over the last couple years. And so what these studies have shown is actually kind of a pros and cons effect to increase CO2 levels. So the new experiments are handled completely differently. They have taken aquariums and then just upped the CO2 levels associated with those aquariums over a longer period of time, so you can allow the water to naturally get more acidic and then watch what happens to the sea life as a part of that acidification increase. And so what they found is that, yes, there are certain species that couldn't handle the acidification, and these include coral reefs, right? So coral reefs do really bad in increased acid levels. However, other species did really, really well. And so there was sea urchins, crabs, lobsters, calcifying algae, and krill actually ended up not only living, but also flourishing and getting substantially larger. So again, if you go back to the paleontology and you go look at history, right, we know that many species in the ocean were much larger in the past. And so all this shows is that some species do better in low acid levels and other species do much better in higher acid levels. And so there's this pro and con that we don't really talk about. Now, our fundamental understanding of ocean ecosystems today is that the coral reefs are the foundation for most ocean ecosystems. And I'm not going to deny that. That's an important thing, and ocean acidification is going to cause problems with that. And we can control, if we can control the CO2 levels over the next 20, 30 years, if we help a lot of the third world countries, second world countries, I don't know what you call them these days because they're not really third world, but you look at India and China and all these next world countries, and they output a lot of these greenhouse gases versus the first world countries. So you look at most of Europe and America, our CO2 levels, we're actually doing a good job at curving how much greenhouse gases we're dumping to the atmosphere. If we help these other countries, then you won't have as much CO2, which means you can slow down the acidification of the oceans, which could allow the oceans to adapt much substantially better, again, potentially allowing other species to become the bedrock of the ocean ecologies, not just the coral reefs. But again, pros and cons, understanding that some species will do very badly in increasing acid levels and other species will do really, really well in increasing acidity levels of the oceans. Okay, so our real goal should be trying to understand where we can make positive impacts to the ecosystems that we have, as well as minimize our greenhouse gas effect. I think that's something that we should probably do, absolutely. But we really need to understand that there is inevitable change, and since change is inevitable, we should just be focusing on allowing the ecosystems to get through this change, rather than trying to prevent the change entirely, because I don't think we can necessarily prevent it entirely. So let's get to the last section on CO2, which I think is important. So what is the lowest limit of CO2, which is why I think trying to scrub CO2 out of the atmosphere is a bad idea, and what is the highest rates of CO2 that we could see that could potentially be dangerous, and is there a chance of a runaway greenhouse effect? So there's this thing there's a guy named James Lovelock, and James Lovelock is a famous scientist, and one of the things he talks about is the Lovelock Limit. So the Lovelock Limit says that if CO2, based on understanding C3 and C4 metabolisms of plants, if you got under 150 parts per million, essentially no C3 plant life would survive. So that's 85% of all plants. And then the 15% of plants that would survive would get diminishingly smaller to the point of not being able to maintain a healthy biosphere. So essentially, you're talking about a mass extinction event at 150 parts per million. Now, the last ice age, we got very, you look at the record of CO2 across this planet. One of the lowest times in our history for CO2 was during this last ice age. We got to 180 parts per million. 180 parts per million. You're talking about 30 parts per million away from hitting that lower Lovelock limit, which could have ended all life on this planet. So I don't think 400 parts per million is a dangerous place for the planet to be at. I think there's a lot of evidence to say that even a little higher than that is probably healthy for us. But we really got to be careful as a species to understand that taking CO2 out of the atmosphere is a very tedious, careful thing, because there is a lower limit where you can cause just as much damage by taking too much out than having enough for the biosphere to survive. So again, I really want to emphasize, CO2 is not a demon. It's not a bad guy. It is what has allowed life on this planet to exist, and we need to maintain CO2 in our atmosphere. The question is how do we allow the natural balance to maintain equilibrium without necessarily having humans cause too much of an imbalance to increase, global temperature changes over a short period of time. So lastly, I want to talk about the whole concept of a runaway greenhouse effect. Okay, so many people look at Venus and say, hey, look, Venus, we could end up like Venus. Well, the first thing I want to cover is, as of today, Venus has 290,000 times the CO2 that Earth does. That's a lot of CO2, and there is no way at current record that we could go and produce those levels of CO2 in our atmosphere. And even during the pre-O2 stages, even prior to plant life consuming CO2 and generating O2, back when we had higher levels, about 219,000 parts per million, 219 parts per million, we didn't see a runaway greenhouse effect. So you can safely say that CO2 could get up to 200,000 parts per million in our atmosphere, and we most likely won't experience a runaway greenhouse effect. No, but why is that? If we got higher levels of CO2, obviously we would potentially have a runaway greenhouse effect. Well, no, we wouldn't. Back to the whole climate system, you start getting those higher levels of CO2, you end up with global, overall warmer weather. You're going to end up with more precipitation in the atmosphere. You're going to end up with higher cloud coverage. That higher cloud coverage is going to stop the solar radiation. So you're going to end up with significantly less solar radiation, even if you could get to levels of much higher CO2. The other thing is we're twice as far away from the sun as Venus. In terms of proportional distance to how much solar radiation we get literally half the solar radiation that Venus does. Which means if Venus could start a runaway greenhouse effect at 200,000 parts per million, then we would potentially need double that or more to start a runaway greenhouse effect because of our distance away from the sun. So for us to have a runaway greenhouse effect, two things would need to happen. Number one, we need the Earth to move significantly closer to the sun so that we can end up with significantly more solar radiation. And two, we would need massive amounts of CO2, potentially more than we've ever had in the history of this planet, in our atmosphere, which are both very unlikely scenarios. So the likelihood of humans over the next couple hundred years causing a runaway greenhouse effect is pretty much zero. Anyways, so I hope we've kind of done a good job at covering that stuff today. So again, today, what did we discuss? Well, we discussed concerns about the climate changing. There are some very serious concerns, and we'll cover a lot of that stuff in the next episode. Understanding why data is good, because good data allows us to have good policies. It's not good to make all of your decisions on bad data or just like runaway greenhouse effect. It's not conducive to the success of us solving this problem by saying CO2 is the evil bad guy and we're going to end all life on this planet and there's going to be this runaway greenhouse effect and we're going to look like Venus. That's not even on the table. We shouldn't talk about it. We shouldn't care about it. It's not a concern that we should have. We should be focusing on the real problems that we can solve and the real impacts that we can make as a species on this planet. Okay, we did take some time to understand how the global climate systems work. We understand that H2O, kind of the big dog in the room, he manages all of the temperatures across the planet, especially the higher end, as the temperatures go up over time. We also understood that we're probably not going to slow down climate change, or we're not going to stop climate change. We can slow it down. We can slow it down. We just won't stop it. And slowing it down is important because that allows all of the species on the planet to adapt. It also allows us as a species, as humans, to adapt substantially better because most of our cities are on port cities. Most of the human populations live next to the ocean, and if ocean levels go up, then we have to move our cities. Now, we'll kind of cover that in the next episode because I think we have a lot of time to do that. I think time is our friend in this particular case, but it is a very real threat. We did understand that CO2 does have an impact, and it is at that stage in the climate where it has the greatest impact, but that impact is minimized to this specific time period based on where we are in the climate cycles. And we talked about how CO2 is really important for a healthy biosphere and that we need to stop demonizing it because too low is too bad, too high is probably improbable, and there is probably a healthy region somewhere in between that allows for a maximum healthy biosphere across the entire planet. Okay? So, hey, I hope you learned something. I hope you found this episode valuable. Next week, we're going to continue to look into the data because I think continuing to look in the data is really, really important. And we will understand better some of the repercussions of climate change because, as I said before, with rising sea levels, there are a lot of problems. But the question I have is there's a lot of predictions that the models make. So if you look at the predictive models today, they talk about increasing storm systems. They talk about more global fires. They talk about famines. So there's a lot of predictions that these models make, and we will look at the data to see how the data fits the potential predictions over the last 20 to 50 years. In addition to that, we'll also look at what some of the biggest challenges humanity will be facing, as well as what some of the best opportunities for solutions to the problems that we have will be in the near future. Okay? So, hey, thanks for listening to today's podcast. I hope you enjoyed it. Again, I hope to see you next week. And if you haven't seen our last episode, please feel free to go check us out on Apple, iTunes, or on YouTube. Hey, thanks for joining us on Perspectives.